Okay, guys, just to continue on. We just talked about the idea that stars vary in color, and that variation of color has to do with surface temperature. So, color is surface temperature. Now we have to think about brightness. And so, with brightness of stars, this is an obvious thing to see. The ancients saw this, and the ancient Greeks were people that were very intrigued in using mathematics to describe things. And so these ancient scholars were very interested in knowing how to apply numbers in this essence of the variation of brightnesses of stars. And so what they did is they assigned numbers. And we call those numbers magnitudes. And it seems to be a little counterintuitive for how they applied this, a little bit different than what we would imagine. They said that a star of a certain brightness was 1, and as they would get dimmer, they would assign numbers of 2, 3, 4, 5, and 6. And so where this is counterintuitive is that the bigger numbers are dimmer and the smaller numbers are brighter. Seems a little bit counterintuitive. And of course, this is what's known as a relative scale. We assign one star a certain brightness, and then we assign these other magnitudes, that's what they're called, to stars that are a certain amount dimmer than the one before that. And it turns out the way that this is done is that, and how they're related in brightnesses, is that a 2 is 2.5 times dimmer, 2.5 roughly, dimmer than a magnitude 1. So a magnitude 1 is 2.5 times brighter than a magnitude 2. Magnitude 2 is 2.5 times dimmer because it gets dimmer to the bigger numbers. And then a magnitude 3 is 2.5 times dimmer than a magnitude 2. And a magnitude 3 is 2.5 times dimmer than a magnitude 1. So they just multiply one another. That means the magnitude 1 is 2.5 times the brightness, roughly, of a magnitude 3, and so forth. The way that these numbers line up is that one magnitude in difference, again, is 2.5 times roughly difference in brightness, either brighter or dimmer, depending on which number you talk about. It turns out that 5 magnitudes is 2.5 times 2.5 times 2.5 times 2.5 times 2.5, 5 times, and that's roughly 100 times difference in brightnesses. 10 magnitudes, because it's the way it's worked is 2.5 times 2.5 times 2.5 times 10 times is about 100 times 100 times difference in magnitude, which is about 10,000 times difference in magnitude between stars 5 magnitudes apart. Just to continue this, 15 magnitudes difference in magnitudes between the brightness of 2 stars on this scale is 2.5 times 2.5 times 2.5, 15 times, which is 100 times 100 times 100, which is 10 to the 6 or 1,000,000 times difference, and so forth. So this is how those numbers work. So, when they assigned the scales, the only only way that they could observe the sky were with these optical instruments called eyes. Today, of course, we have telescopes of all sorts of capabilities. Some can look at visual light that we use with our eyes and can see with our eyes, whereas other telescopes, can see radiations, part of the electromagnetic spectrum, that our eyes are not sensitive to, such as radio waves, or X-rays, or gamma rays, microwaves, and so forth. And so only speaking about visual radiation right now, meaning what our eyes can see, we have these telescopes that, they're light buckets. So we've expanded the scale to go into dimmer objects that we couldn't even see with our eyes, because 6 of magnitude 6 is the dimmest that we can see with the eye. Anything dimmer than that basically are not visible with your eye. And because this scale didn't include objects such as the planets or the moon or the sun, we've had to expand this into the negative numbers. So the more negative the magnitude, the brighter it is. Seems again counterintuitive. Hey guys, tell me something. What's dimmer? A magnitude 2 star or a magnitude -2 star? And of course the answer is, as you go into bigger numbers, it's dimmer. So the magnitude 2 star would be dimmer than a magnitude -2 star. Make sure you understand that. So we have this means of assigning numbers to the brightness of stars. And it turns out that we use in astronomy 2 different magnitude scales that are used all the time. So the first scale is what's known as the apparent magnitude scale. And we denote it with the lowercase m with a subscript v, and the v just means that we're looking at the brightness and giving numbers for the brightness of objects, looking at their visual radiation. In other words, we're not looking at X-rays or radio waves or anything like that. We're looking at the radiation that we would see with our eyes. So the subscript v just means visual light that we see with. And so with this scale, it's just us walking out in the sky and saying, okay, let's see, that star is a magnitude 2, that's a magnitude 1, that's a magnitude 5, or even looking through a telescope at stars we can't see with our naked eye and saying, oh, that star is a magnitude 7. The reason why it's 7 is 2.5 times dimmer than that magnitude 6, which we could see with our eyes on a really clear night. Remember, all these magnitudes that we assign stars is assuming that the Earth does not affect things at all. In fact, it's as if the Earth is not even here with all the smog and the city lights and whatever water in the atmosphere. It's like we're out in space and assigning those numbers by what we see with our naked eye. So again, this is assigning by what we see. So this is just assigning numbers using our eyes. Or imagine if we could see them, if it's too dim for us to see with our eyes, assuming we could see them, we can assign these numbers even for stars that are much dimmer than visible ones for us. Is that clear? We're just assigning this as if we can see every star and then just comparing how bright one star is to another star on that scale. And of course, to start this off, we had to assign maybe a magnitude 1 to a particular star. So we just say, oh, that's a magnitude 1. Oh, that star over there is 2.5 times dimmer than that, so it must be a magnitude 2. Oh, that star is 2.5 times dimmer, that must be magnitude 3. And so we're assigning that number to a star and then just relating all the other stars' brightnesses to the particular one that we've assigned that magnitude 1 to. Now, when I do this with the apparent magnitude scale, it's just a scale I can see with my naked eye. So if I walk out and I think, what affects the brightnesses of the stars in the night sky? And remember, the Earth does not take part in this. It's just the fact of something to do with the universe and the stars. Well, certainly one thing that would affect how bright things are is if there's a star close and a star that's far away. That will affect how bright things are. even if they're the same type of star, if it's close, it's going to be bright. If it's far away, it's going to be dim. And so that will affect their magnitudes that we assign. But also remember this, we could have a really bright star farther away and a dimmer star that's, or not as bright a star close by, or not as, whatever makes a star bright. And this star could be actually looking brighter than that one, even though it's farther away. So there is complexity, but certainly distance matters. So this apparent magnitude scale, one of the things that would affect this is the star's distance. And when I say the star's distance, I mean their true distance, which we assign to be the symbol r. How far the stars are truly from us. What else can affect the star's brightness? Well, as it turns out, we reside in a galaxy type called a spiral galaxy. And in spiral galaxies, you have this central region called the core, and spiraling off are arms. Now, this is only 2 arms spiraling off. You can have more than that. And this is loosely spiraled arms. Turns out that we're going to find out that how the arms spiral away can differ. And we'll talk about that in an upcoming unit that I hope we get to before the end of the semester. Turns out that we're way out here on one of the arms of a spiral galaxy. So we're in the boonies. And it turns out in spiral galaxies, there's lots of gas and dust. Hey guys, imagine this is a dark and stormy, well, it's not a stormy night, it's just a dark night. And let's imagine that toward the ocean, about maybe a half a mile from us, where we can see it somehow, would be a lamp of a certain brightness. And then in the opposite direction from the ocean is another lamp at the same distance from us. And both lamps produce the same amount of light. With the ocean, ever so often, a fog rolls across the land emanating from the ocean. And let's imagine that fog covers the lamp that's closest to the ocean. Well, with the fog rolling over it, it'll dim that lamp for what we could see. And if the other lamp that's not being covered and is farther from the ocean, still not at all being covered, and there's no fog in between us and the lamp, the one that has no fog would be brighter. So if I'm right here in the Earth, and here's a star out here, but there's a lot of gas and dust in between me and the star, that will dim how that star looks. And so that's going to affect what I assign in this apparent magnitude scale. So any intervening gas and dust will affect. And we will have to talk about that gas and dust very soon when we talk about the birth of stars. But that's going to affect how bright things are. Now, one thing about this is that certainly, stars differ in multiple ways. But imagine this. Tonight, if you're studying, because what else do you have to do? We are not traveling around too much, are we? But tonight, when you're studying, what type of lamp do you study under? Do you study under a 5-watt lamp bulb, or a 75-watt lamp bulb, or equivalent 75-watt light bulb? Now, sometimes I've asked students, hey guys, which one do you study under? And there's absolute silence. And when I get that, I think, oh my goodness, I am teaching royalty. They don't understand that light bulbs vary in how bright they are. They must have other people dealing with the lamps in their homes when they blow out. They must have servants because they're royalty. And so they don't have a clue about this. Now, many of you do because you don't have servants. You're like me, not royalty. But some of you may be, and so when a light bulb goes out, you call your servant over to change it for you who knows about light bulbs, Oh, by the way, what you say is, hey, Mom. And then they come and serve you by changing the light bulbs. But light bulbs vary in how much light and heat they produce. And the same thing is true with stars. Stars vary in how much energy they give out into space. And that has a name. Stars vary in luminosity. What that is the energy that they emit in space that passes through from their cores through the star out into space, and that's the energy that is given off. Now I'm going to speak more about this in just a little bit, about this term of luminosity. It's very important. But all that is how much energy a star produces. And then finally, guys, imagine this. Let's see, I always have something on me that I can bring in here. Here's a little flashlight. So imagine, you look at this flashlight, it's pretty bright. And it's pretty bright. If I put it in your eyes, you'd probably say, get back, buddy. Leave me alone. But imagine if this light bulb, or excuse me, the flashlight was multiplied by 1 billion times. How bright that would be. So certainly another thing that will affect how bright things are is the star surface area, because stars do vary in their sizes. And so because of that, these 4 different things, their distance from us, their true distance r, there's gas and dust intervening between us and the star, luminosity, how much energy a star is actually put into space, and finally their surface area, will define how bright a star will look like when I look at it in the night sky. And that's what the apparent magnitude scale basically brings in as we assign numbers for just by using our eyes and giving those numbers to that. And we use this often. It's kind of useful. But there is a problem here as a scientist. See, as a scientist, what I want to do is I want to compare the brightnesses of stars because of their own properties and not something external to the star. And so that way, when 2 stars vary in brightness, it's because it's something inherent has to do with the stars themselves. And there's 2 things here that certainly doesn't belong about the star itself, and that is, well, dang it, how far is the star from us? It has nothing to do with the star itself. It just happens to be to do with how where it is at compared to where we are at. Nothing to do with the star. And of course, the other thing that has nothing to do with the stars, if there's any gas intervening between us and the star. It's not even a part of the star. So that doesn't matter as far as the star is concerned. So the point here is that when I assign the apparent magnitudes, it doesn't give us a big insight a lot of times in the stars themselves. And it would be nice to have a second scale, magnitude scale. This is the apparent magnitude scale. But it would be nice to have another scale that only brings in to it the idea of properties of stars themselves. And there is a scale like that. So let me go ahead and erase some of this stuff. And I'll talk about the second possible magnitude brightness scale that we could use in astronomy, and it's used quite often. And so this one right here, let me use pen, is called the absolute magnitude scale, as opposed to the apparent. Apparent is just what it apparently looks like when we see it. This is the absolute, and this is denoted by a capital M, subscript V. The apparent was little m, And the V, of course, still refers to the fact that we're looking at visible radiation, light. And so with this is what we do. So here I am looking at two stars. Star 1, star 2. And let's say that there's gas and dust out here. Gas and dust. And so what I can do is I can get their apparent magnitudes, little m1, little m2. So I have their apparent magnitudes that again reflect their true distance, reflect the fact there's gas and dust there that will affect their brightnesses. That also brings in the idea that they may vary in luminosity, how much energy and light they're producing and spewing into space, and also their surface areas. But we want to get rid of the effects of gas and dust. So the first thing that we do is, let's say we get rid of the gas and dust. And so the gas and dust has a name. It's known as the interstellar medium. Very important. And we'll talk more about that later. That's called the ISM. And so one of the things we want to understand is, number one, just how thick is that ISM in our space and that within our galaxy, and how does it reduce the light of a star? So these are big areas that we study and we still have a lot to learn about that. But let's say by different means we can subtract the effects on the brightness of the stars because of the gas and dust, and therefore adjust their brightnesses or their magnitudes to get rid of that gas and dust. So look at this. If I let me explain that. If I look at star 1, it turns out that I'm only looking through a little bit of gas and dust, whereas if I look at star 2, I'm looking at through a lot more gas and dust. So if I just ripped away all that gas and dust and got rid of it, what would happen to the brightness of the stars? So to get rid of this, to rid ourselves of the gas and dust, I would have to adjust the stars' apparent magnitudes. And of course, will the stars get dimmer or brighter if I got rid of the gas and dust? And the answer to that, of course, is that it would get brighter. So we would have to adjust the magnitudes more negative to make it brighter. But we adjust the magnitude for star 2 more negative, much more than star 1, because we're looking through a lot more gas and dust, and therefore it will be dimmed much more by the gas and dust than star 1. So I'll say it again. Because we're looking through a lot more gas and dust to star 2, we have to adjust its apparent magnitude brightness much more than star 1, since we're only looking through a little bit of gas and dust. And then we adjust the magnitudes more negative, because by getting rid of the gas and dust, the brightnesses of the star will be brighter. It'll be increased. And remember, with magnitude, the more dimmer it is, it's it's a bigger number. To go brighter, it has to go toward the negative numbers. Do you see? I hope that's clear. So we get rid of the gas and dust now. But then the next thing is we want to rid ourselves of distances. In other words, differences in the distances of stars. So we assign a certain distance from us as the distance we want to be at. And so that distance we assign things to is something called 10 parsecs. Let me explain what a parsec is. We have to kind of do a little dance and waltz of definition here. To understand this, I first have to define a different distance. And so what that distance is 1 light year. And what that is, it turns out to be the distance light travels in 1 year, which turns out to be about 6 trillion miles. Which is, just so you write it, 6,000 million billion trillion miles. So that's a unit we use for galactic distances simply because galaxies are huge. Our galaxy's roughly 100,000 light years across. How would you like to write 100,000 times that in miles to give the size of our galaxy? I'd rather write light years. And it turns out the distance that we use, which is called the parsec, is equal to 3.26 light years is equal to 1 parsec. A parsec means 3.26 light years. PC is just a simple way of writing parsec. Make certain you understand that. I'll explain where that comes from in just in another lecture or so, where we get this weird term or unit called the parsec. 3.26 light years is 1 parsec. So basically what we do then is we assign a distance. It's just arbitrary, is what we choose, for the absolute magnitude to be 10 parsecs. And I'm going to say something more about that soon. So what do? We've already adjusted the apparent magnitudes of star 1 and star 2 to get rid of the gas and dust. It's gone. Then what we do is we adjust those new magnitudes to make it so that the star is at 10 parsecs. So this star is going from farther away and it's being pulled in closer to 10 parsecs, and therefore it's going to be brighter because it's closer now. It's closer to me. If it's brighter, then we're going to have to adjust the magnitude again more negative to make it brighter so that it would reflect the distance of 10 parsecs. What about star 2? Star 2, we have to adjust the brightness to make it farther away from us than what it really is. And so that brightness then would have to be dimmer because it's farther away, which means we have to adjust its magnitude more positive to make it dimmer. And that way effectively make them all at 10 parsecs. So if I asked you 2 questions. I think I've got gardeners out here. Of course, they come right at the time I'm lecturing, but that's how things are, right? We don't have the construction people now outside building the new building. They're still working on that, by the way, and making progress. But we still have to deal with things like gardeners. But the point here is this. Let me kind of recap this. For the absolute magnitude, every star will be at 10 parsecs. So a close star will be taken out farther, made dimmer to make it farther looking. Every far star is pulled in to make it closer, therefore brighter looking. And every star is at the same distance, 10 parsecs. And now, the only thing that will vary in those 4 items of the apparent magnitude. Remember, the apparent magnitude was gas and dust can affect the brightness, gone. The other thing that could affect brightness is some stars are close, some are far. Now they're the same distance, so that thing's gone. So the only thing that's left now that will affect the magnitude assigned in this scale is the luminosity and the surface area of a star. That's the only thing that will be affect the value for the absolute magnitude. Because we got rid of gas and dust by adjusting magnitudes, we got rid of star distances to be the same distance, d of 10 parsecs, by adjusting brightnesses again. And those are the only thing that now differ from star to star. So that's kind of neat. What that means is that if stars vary in absolute magnitude, it must mean that they vary either in their luminosity or surface area or both. And now we can really compare stars and look at them to get a better understanding of how stars vary from one to the other. So let me recap this a little bit. One thing that we have here is that we can assign numbers to denote the brightnesses of stars. And this has been brought down through the thousands of years since the ancient Greeks. And we just have accepted their system. We've expanded their system to reflect the idea that we want to have dimmer objects within our scale that we can't see with our naked eye because we can see them with telescopes. And we want to bring in bright objects that we did not originally include. And so we've expanded the scale. We said that we have two scales that we can use. One is the apparent magnitude scale, the other one is the absolute magnitude scale. And the apparent magnitude scale is just us looking at them. So if I asked you what distance is related to the stars in the apparent magnitude scale, it is always their true distance. That's the apparent magnitude scale, their true distance. If I ask you what is the distance related to the absolute magnitude scale, every star has been adjusted to be as if they are at 10 parsecs. So don't get lost in the details. If I ask you, what are the things that affect the brightness in the apparent magnitude scale? The scale number 1 was gas and dust presence, the distance and their true distance from us, their surface area, and their luminosity, how much light and heat they produce and put out into the universe. If I ask you what are the things that affect the brightness within the absolute magnitude scale, it's only two things related to the stars themselves. The absolute magnitude is related to luminosity, how much energy and light it produces, and their surface area. And so that's how we relate these two scales. I hope that's clear with this. Now let me say something really quickly to end this particular video and on the idea of luminosity. I'm going to go ahead and erase this. I'll leave that there so we can pause it easily and take a look at this. I know there's lots on there. I'm so sorry. I wish I had a bigger, I'm used to a large whiteboard. I've got my baby whiteboard. I will never look at this room again in my house. I'll shudder a little bit as I've had to go through all my lectures here. You'll probably shudder too if you saw this whiteboard after this stuff. Come on, we'll shudder together. So let's talk a little bit about luminosity. Guys, pardon me, I'm going to close my door. I'm certain they're going to be out here blowing soon. Try to make it quieter. one thing that even in the midst of a pandemic, got to have our yards looking good. I tell you, Southern California, and that's good. Makes me happy that people are making money at this time. It's a very tough time for people. So, the luminosity is defined to be this. Has a symbol L. And so, let's say that this is a star surface. We take a little bit of surface area, 1 meter by 1 meter. So the surface area is 1, the area is 1 meter squared. The luminosity is how much energy, that means how much light and heat that basically comes out of the star. Really is light, because that's what travels from the star to us to heat us. And we know that light carries energy. If you don't believe me, we're getting some nice, beautiful skies and days out there. Go outside and stand outside for 8 hours without any sunblock. Don't do that. It will be uncomfortable because you get burnt from the energy of the light of the sun. And so the luminosity is how much of that energy of the light comes out from every square meter for every second of time. That's the luminosity we use. And so we use another rule, and it was developed about the same time as Wien's law, that can give us the luminosity. And the way that we do this is what's known as the Stefan Boltzmann law. And, you know, I am certain your textbook gives the full equation. All I'm going to say is that the luminosity is related to the surface temperature to the 4th power. Oh, so that says that how much energy that comes out every second from every square meter of the surface of a star is deeply related to how hot that star's surface is. Remember, what's the hotter star? It's the blue stars. So blue stars will have a tremendously greater amount of energy flowing out of its surface every second out of every square meter because they're hotter. And so let's see what this means. So you'll see the full equation in your book. I'm going to relate this so that we can kind of relate what this means. And this is what you could be held accountable for. So I'm going to look at 4 different stars, and then you can compare how much the luminosity changes compared to the surface temperature. So let's just do it once, one after another. So you got that right now. I'm going to go ahead and erase this so I have plenty of room. We're going to talk about the Stefan Boltzmann law. Stefan Boltzmann law. Again, what that says, the luminosity is related to the surface temperature to the 4th power. So here's star 1. Let's say its surface temperature of star 1 is 4,000 Kelvin. This is a red star. I'm not going to use, 4,000. I'm just going to give it a value of 1 to make this easy. Therefore, the luminosity of star 1 is related to its surface temperature of star 1 to the 4th power, which is 1 to the 4th power. Well, guys, what's 1 times 1 times 1 times 1? Well, obviously it's 1. That doesn't tell us anything. Let's now compare that to a hotter star. So star 2, its surface temperature is 8,000 K. So this star is a reddish star. This star is brighter than our star. It's hotter than our star. Probably an F star. But we're not going to use 8,000. It's twice as hot as the 4,000, so I'll make it a value of 2. So I've doubled the temperature from star 1 to star 2. And its luminosity is, again, related to its temperature of the surface to the 4th power, which is 2 to the 4th power, which is 2 times 2, that's 4, and 2 times 2 is 4, so 4 times 4. 2 times 2 times 2 times 2, 16. So look at this. What that says is that if I double the temperature of a star, the amount of energy coming out every second from every square meter is 16 times greater than this cooler star. Excuse me. Let's do another star, star 3. In this star, its surface temperature is 12,000. Okay, so maybe we're getting up into like an A star, kind of a brighter star, a hotter star into the bluish range. Of course, that's 3 now. It's 3 times that original temperature of star 1. And its luminosity is its surface temperature of star 3 to the 4th power, which is 3 to the 4th power. So that's 3 times 3 times 3 times 3, which is 9 times 9, which is 81 times. So you can see as we increase the temperature of a star, the amount of energy that flows out of every square meter every second increases tremendously. Let's talk about one of the hottest stars you might see. So this will be the last star, star 4. The temperature of this star is 40,000 Kelvin. That's 10 times as hot as that first star. So its luminosity is related to its surface temperature to the 4th power, which is 10 to the 4th power, which is 10 times 10 times 10 times 10, which turns out to be 10,000 times as much energy is flowing out of every star. And this would be an O star, one of the hottest O stars, which is the hottest star within the spectral classes. So this could be a K or M star spectral class. This could be a star. Excuse me. Let me say it correctly. This is a K or M star. This is probably an F star. This is probably an A star. This is probably an O star in the spectral class ranges of temperatures. And one thing about this, the hotter the star, it turns out, are bigger stars. So these cool stars, not only do they not have a whole lot of energy flowing out of every square meter, but also it turns out that they don't have as many square meters compared to these hot stars, which has tremendous energies coming out compared to that cool star out of every square meter every second, but there's a heck of a lot more square meters. And that's one of the reasons why when you go out at night, most of the stars you see are bluish white stars because they're just dang bright that even if they're far away, you can see them because they're like lanterns, bright lanterns in the night sky. And that allows you to be able to see them far away. And that's why you don't see too many red stars, just because they're just dang dim. They're not very visible because they're not, they're shining with very much reduced energy compared to the hotter stars. So that talks about the brightness of stars. So where do we go from here? Well, on Earth, we know something. We know that when things get hotter, they generally get brighter. And when things get cooler, they generally get dimmer. And we can relate that to the laws of physics we know on Earth. So the question is in space, do the same rules hold? And we can say, sure they do. But see, we can't jump to conclusions like that. Who's been out in deep space at other stars? Not even to the closest stars. Not even the closest stars. So who is to say? We have to verify that that's the case. That, that like on Earth, when things get brighter, they get, hotter, or vice versa. If they get hotter, they get brighter, and vice versa. They get less hot, they get dimmer. I mean, my goodness, there could be unicorns in space, meaning magic out there, and things could work completely different than on Earth. Now, we don't, as scientists, we don't say there's magic out there. What we say is, well, what's the rules in space that are obeyed that are not obeyed here, and why? What are the new rules so we can understand the universe? And so that's how we look at this. So what we're going to do in the next video is to describe how we can utilize our understanding of stars to come up with the answer, are there unicorns in space? In other words, do the laws and rules of physics that hold on Earth and in the close regions of space around us hold in deep space? And that's what we'll talk about next time. Okay, guys, take your time, go through this, make notes. If you have to go back in the video, re-listen to it. Carefully understand by reading. If you can read my writing, you poor people. Here you are, you're stuck at home. But not only are you stuck at home, but my goodness, you got to read my writing still. Will the pain ever end? I don't know. But I'm here if you need any help. Talk with you soon, guys. Bye-bye.